Okay, so I have to finish this little exercise here. I have asked you to try to do by yourself. And you will see that this result will be the keystone of one of the two important results we are going to see in the chapter 3. That will be fundamental for the financial part. And this result is called the Girsanov theorem. So the aim of the Girsanov theorem will be, so we are going to see today the definition of the Brownian motion. You will see that if I shift the Brownian motion, I don't have any more a Brownian motion, but it's possibility to change the probability in order to make a shifted Brownian motion to a Brownian motion. Okay, it will be very important in the framework of the Black-Scholes model, and the little result that is below the theorem is exactly this one. What I do here, I start from a Gaussian distribution with mean m and variance sigma square, and I want to change the probability in order to make it n0 sigma square. I want to remove the mean. Okay? I want to remove the mean. So it's exactly what we are going to see today. Okay, so what is this? I start from x that follows the n m sigma square and the p. Okay? And I want to find a probability q equivalent to p, okay, such that x follows under this new probability n0 sigma square. And you have in the statement everything here. Okay? So I define the new probability by its density function, dq over dp. I call it L, and it's equal to what is written on the board here, that is exponential minus mx over sigma square, okay, plus m square over 2 sigma square. And what I want to prove? I want to prove that x follow the n0 sigma square under this new probability q. Okay? It's what I want to do. Yes? Ah bah on vous donnait la densité pour changer de proba. Bah, pour la trouver tout seul, c'est un peu compliqué. C'est pour ça qu'elle a été donnée. So, I want to check that a random variable follows a Gaussian, n0 sigma square. So what are the tools you have in order to check if someone is a Gaussian random variable or not? So typically here you see that the change of probability is an exponential. So it seems to be not that stupid to use the characteristic function, because in order to change the probability I will have an exponential. I have already an exponential in the characteristic function. So it's not that bad to do this way, okay? So I am interested in computing the characteristic function of my random variable under Q. Okay, it's what I want to compute. My hypothesis is that I know something about, first, the change of probability, and also about the distribution of capital X under P. So first, I can change my probability here to write my expectation as an expectation under P. And why I do this? Because I have an hypothesis here. I follow this one under P. So it's what I want to use. So I change, and if I do this, I pass from an expectation under Q to an expectation under P, okay, multiplying by dq over dp. It's what we have seen during the previous session. And write it this way. Okay? And I know perfectly what is dq over dp. It is exponential minus mx over sigma square plus m square over 2 sigma square, and I have to add plus I tx. And what we are going to use? We are going to use the fact that I know that what happened for the characteristic function of x under p. Okay, that's what we are going to use. So first, here I have a constant that I can remove from the expectation. I have this one, okay, and I want to compute this. So I can write it this way. Exponential of I, x, and someone inside, in order to use what I know about the characteristic function of x under p. Okay? So I have what? I have t, that is the term coming from this expression here, and I have also this one, and if I want to make appear this one, okay, I can write it as plus I m x over sigma square. Okay? Because I don't have the x here. If I do this, I will have I squared that is minus 1, and so I obtain exactly this term here. Okay? So now I use my statement. My statement that tells me that x follows n m sigma square under p. So it means that I know the characteristic function of x under p. What is it? I know that if I want to compute this kind of term here, write it this way, I t x, okay, I obtain what? What is this?
The power of sigma squared t squared.
And
what?
I have two terms.
But it's a standard one?
So exponential itm.
I wasn't standard.
No, it's not standard, it's n sigma square here. And les deux sur deux. I repeat that it's something that you have to know perfectly in this course. You are going to use it, okay, 100 times. Black Soul, ça sera gaussien, donc s'il y en a une à savoir, c'est celle-là. Want to know this one in this course, okay? And in general, it's the only one we know. Okay? We are able to recover the one of the other one, but this one we don't have to be able to do the computation anytime, okay? Typically for an exam. Okay. But I can replace. I will put this one instead of t. Okay, so let's take one t equal to t plus I n over sigma square. Okay. If I plug inside, I obtain what? That the expectation under p of exponential I t plus I n over sigma square x is equal to the exponential of I m multiplied by t plus I n over sigma square minus sigma square t plus I m over sigma square over 2. I just plug inside to see what happens. Okay? I have this expression here, and I make appear what I want, that is this term in the moment generating function of x and the p. Okay? So I can simplify a little the things, a priori. So I have exponential I t m. I have I squared that is minus m squared over sigma square, and I have to develop the square. So I obtain minus sigma square t square over 2. I have the double product, and I obtain minus I t m. Because I have simplification, okay, it comes from the double product here. 2 times t I m over sigma square. I multiply by sigma square and I divide by 2. So I obtain this one, okay? And then I obtain what? I have I square minus 1, so I have a plus, sigma square, m square over 2 sigma 4. Okay? That is sigma square square. Okay, so at this stage, is it possible to simplify a little? Yes. I have this one that simplifies with this one. Okay. And I will continue here. So I have this exponential before, I don't have to forget. That is exponential m square over 2 sigma square. And the term I have computed just before here, that is, so I have what? I write everything. So I have minus m square over sigma square. I have minus sigma square t square over 2. And I have plus m square over 2 sigma square. And I have some simplifications here. I have this term before. I multiply by what I have computed here. And I obtain at the end what? You see that you have m square over 2 sigma square plus m square over 2 sigma square minus m square over sigma square. So you have, and at the end, you obtain exactly what you want. That is exponential minus sigma square t square over 2. And so you have done the job. You have proved that under the new probability Q, the moment generating function of x under Q is given by exponential minus sigma square t square over 2, proving that under Q, x follows n0 sigma square. It's exactly what I want to prove. Okay? So you see that you have a way here to transform the initial probability into an equivalent one in order to make nm sigma square n0 sigma square. You make the mean disappear. And you will see that in the chapter 3, I repeat, in the Girsanov theorem, we are going to do exactly the same way, but dynamically, because instead of having a single random variable, we will have a ground motion. Okay? And we will be able, using this result that will be the keystone of the argument of Girsanov, okay, we will be able to obtain, changing the probability, okay, a shifted ground motion that becomes a Brownian motion. Okay, but we will see this later in November. Okay. So computation, so nothing, if you know the characteristic function of a Gaussian, then you just have to develop a square to do something like this, but it's not complicated. Huh? Okay, let's be careful with the computations, but nothing theoretically difficult. Okay, and you have to know this one. Okay, so it closes the chapter 0. And if you don't have some question concerning this chapter 0, we are going to pass to the chapter 1. That is the one dealing with the probably the most famous stochastic process, okay? Not necessarily in finance, but in time, that is the Brownian motion. So we are going to start the definition of Brownian motion, maybe something that you have already seen for most of you, okay? We are going to see an equivalent definition in terms of Gaussian processes. And once we will have this definition in terms of Gaussian processes, we are going to try to build it. Okay? To build it by using Hilbert spaces tools. And you will see that the definition is not that complicated. Okay? And I will do it in details today. Do you have some questions? No? So for the moment, okay, I switch this part. Okay, so maybe, so you have at the beginning of the chapter 1, okay, an historical explanation of where the Brownian motion is coming from, not in finance, but so read it at home, okay? And I start with the beginning of the chapter with the definition of the Brownian motion. So may I erase the board? So at least this one. Brownian motion that I will denote by Bm from now on, okay? And first, the definition. Okay. So I start, as usual, from a probability space on which I will define all my random variables. So this omega AP will be fixed in the whole chapter. Okay. And I define the Brownian motion this way. So definition 1 to 1. So a Brownian motion or Bt t belonging to 0 capital T is a Brownian motion, okay, if it follows 4 properties. Okay, so it's the definition of a standard Brownian motion here. First, I want to start from 0. No choice for the starting point. Okay, so first, so I will use the same notation, it's small a. B0 is equal to 0, P almost shown. Okay, so B0 is 0 in the sense of probability. Okay, the probability to be equal to 0 for B0 is 1. Okay, it means that if you want to plot a Brownian motion, you start from 0 with this definition. You don't have the choice. Okay. Secondly, if you want to plot its trajectories, they are continuous in the sense of to be continuous for the trajectories of a stochastic process we have seen together. Meaning that the set of the trajectories that are continuous, okay, has a probability equal to 1. Okay, so I can write it this way: Bt is continuous. And remind that I have given a precise sense to what is to be continuous for a stochastic process. It means that the set of the trajectories having the continuity property, okay, this set has a probability equal to 1. Okay? Write it this way, last time. The probability of the W belonging to the universe such that this mapping is continuous, and this set has a probability equal to 1. Okay? So with proba 1, when you draw or when you plot trajectory, you will obtain something that is continuous. Okay? So I start from 0. I am continuous. Third point of the definition is what we call the independence of the increments that tell me that if t should be greater than s this way, then Bt minus Bs, okay, so you have the time s, the time t. Bt minus Bs is the increment of the process on the interval st, final value minus initial value. And I want this increment to be independent of what happened before S. So when you consider the increment of the Brownian motion on an interval, you want it to be independent of what happened before. So I can write it this way. It is independent of FSB, something that I have already defined, that is the filtration generated by a stochastic process, and I just remind you that where FSB is sigma of BU for U It's the smallest sigma algebra that make all the BU measurable for U between 0 and S. Okay? So intuitively, I can describe this saying that when I consider the increment of the ground motion between T and S, this increment is independent of what happened before for the ground motion. Okay? So, if you consider in terms of trajectory, what will happen from S to T is independent to what happened before. Okay? One statement fulfilled by the ground motion. And finally, the fact that this process is related to the Gaussian distribution. If T is strictly greater than S this way, I know the distribution of Bt minus Bs. It follows the N0 T minus S. So I have something that is central, and when I consider an increment on an interval, the variance of the related Gaussian is none other than the length of the interval. So it means that the distribution of B2 minus B1 is the same than the distribution of B3 minus B2. The only thing that is important is the fact that you know the length of the interval under which you take the variation, the increment. Okay? So, if you fulfill these 4 points, you are a ground motion. Okay? So if I ask you to check that someone is a ground motion, you have to check these 4 points in the definition. Okay? So I'll just keep this on the board, okay? Because I have on the I will put the definition here, and in the video you will have this that will appear. Okay? Just to be sure that I have put it. Yes. Okay. So several remarks concerning this definition. So for the moment I keep it on the board, okay, but if you see, if I keep it on the board, I will have this one to finish the course, so I won't do it anymore, but I will keep it on the whiteboard, okay. So some remarks concerning this definition, okay. So here you have simply the filtration generated by the Brownian motion. Okay, I know that according to what I have said in the chapter 0, necessarily the ground motion Bt is adapted because the filtration was built this way, is adapted to the filtration Ft. Okay, because you see that here you have S that is inside it. So Bs is FSB measurable, Bt is FTB measurable. And keep in mind also that from what we have seen together in the chapter 0, I have said that all the filtration we are going to work with are complete, meaning that they all contain negligible sets. In such a way that typically, if I have X that is Ft measurable, Y that is equal to X PL mutually, I want Y to be Ft measurable also. And this is possible, it's a proof we have done together, if I suppose my filtration to be complete. Okay? So, I will always suppose that I have here a complete filtration. Okay, so suppose that you want to prove that someone is a ground motion, so you have to prove that I start from 0, not complicated. You have to prove that the trajectory are continuous, so something is related to analysis. And then I have to prove the independence of Bt minus Bs with respect to this one. So how to do this in practice? Because a priori here, I have a continuum of Bu inside this sigma algebra here. Okay? But it's important to have in mind, so it's a deep result of probability theory that is called the monotone class theorem, but whatever, what I want you to have in mind is what we are going to write now, that if I ask you to prove that BT minus BS is independent of FSB, in fact, what I want you to prove is that BT minus BS is independent of all the random vectors that may be built from the BU. So, equivalently to the fact that for all n belonging to n star, for all, I can write them this way, T1, 3t less than T2, T less than Tn, less than capital T, greater than 0. So for all n and all T1, T2, Tn between 0 and capital T, I can always suppose that they are ordered. Okay, it will simplify the things later on. Okay, if they are not by input order. Okay, and then I want that BT minus BS is independent of the vector BT1. Excuse me, what I have done? It's stupid what I have written here. Yeah. It's 0. It's S here. Okay. Instants that are less than small s, BT minus BS is independent of BT1, BT2, BTN. Okay? It's equivalent. To prove that BT minus BS is independent of FSB just means that BT minus BS is independent of all these kind of vectors of any size with any times being in the interval 0s. Okay? So this is the meaning of this. So I'll just take my notes to be sure not to forget anything. And to prove that I am Gaussian, you prove that you are Gaussian. So you can compute the characteristic function, for example, and prove that it is the one of n 0 t minus s. Okay? And so just have a look on my notes. So for most of you, it's a definition you have already seen. Okay, so where are my notes? Okay. So maybe before to have a look on a definition that is equivalent to this one in terms of Gaussian process, we have already seen together. Just a remark concerning, so you see that in the lectures note, okay, but you have here, I have plot a trajectory of the Brownian motion between 0 and 1. Okay? So if I remind, I have done this with 1,000 points, okay, and I obtained this kind of trajectory for the Brownian motion. So something that is, okay, starting from 0, that is continuous. So I just want to explain to you how to obtain such a plot, okay, from the definition. So I need some place somewhere. Maybe the idea is how to generate the Brownian motion using a computer. Okay, so I just put the definition here. I keep it, and I can erase it here. So suppose that you want to plot the Brownian motion, the trajectory of the Brownian motion using a computer. Okay. So first of all, the Brownian motion is a stochastic process in continuous time. With a computer, you won't be able to do continuous time. It's not possible. Okay, with a computer, you can do discrete things. Okay, so it's not something that is typical to the Brownian motion, but that's true for any kind of process. If you want to represent a trajectory, you have to discretize. Okay, you don't have the choice. So I have to consider discretization, so I can make it start at 0. So you have T1, T2, T3, and the last one that is Tn. Okay? Of course, if I want a nice plot as I have done, okay, I have to take small n that is very big. Okay? So I don't know, for example, you can take, okay, a subdivision with a step size that is capital T over 1000 or capital T over 10,000, 100,000 as you want. Okay, it's very quick to do this, so even 1 million, okay, no problem for this. But the methodology is exactly the same. So the idea is to be able to represent the discretization of the trajectory of the Brownian motion itself. Okay? So to begin with, I don't have the choice. I don't have the choice because B0 is equal to 0. So I know that I will start from 0. Okay? So the first point, I don't have the choice. For the second point, that is with my notation BT2 here. What can you say about the distribution of BT2? You have everything on the whiteboard here. BT2 is a Gaussian with a mean equal to and a variance equal to. So BT2 follows N0 T2. You take just the third and the last point of the definition, take T equal to T2 and S equal to 0. Okay? My daughter that come back school, okay, so nice to. Okay. So if I want to plot one realization of B2, I just have to generate N0 T2. And this N0 T2 may be generated from N01 from this. I can write it as the square root of T2, let's say G1, where G1 follows to N01. Okay? It's the distribution of BT2. You know from the beginning of the chapter 0 how to generate with the computer a Gaussian, N01. You have several methodologies to do this, okay? In the beginning of the chapter 0, I have reminded to you what is the Box-Muller formula in order to be able to generate a Gaussian from two uniform on the interval 0, 1. So you have something. So let's suppose that you are able to generate this Gaussian easily. If you do, you will be able to generate BT2. Okay? So I have my BT2 if I am able to generate G1. Okay? So let's suppose that I do, and I will have, for example, why not, it may be positive or negative, because I have a Gaussian. I suppose that it is here. And I will say that between T1 and T2, my Brownian trajectory, what I can do, I can just consider the piecewise linear approximation. That will be this one. Okay? And then I continue. For BT3, so let's start by doing exactly the same thing as previously. So for BT3, I know exactly the distribution. But I can write it as this one. So what can you do in order to generate BT3? So I can generate a Gaussian, but I have to be careful. I have to be careful because suppose that you take an independent N01 here in order to generate BT3. It won't work if you do this way. Because my G1 and G2 are not independent. They are not independent. If you compute, I will do this in a few minutes, the covariance between BT3 and BT2, you obtain BT2. Implying that G1 and G2 can't be independent because their covariance is not 0. So it means that it's not the good idea here. Okay, so if I want to do this way, I can do the job, but I have to be careful because G2 and G1 are correlated. I have to quantify this correlation and to be able to generate a G2 that is with the good correlation with respect to G1. So it's not the way we do in practice. Because if I do this, I don't exactly have a look on what is the definition of the brand motion. The definition of the brand motion is based on increments of the brand motion, okay, that have very nice properties. So instead of doing this, it's possible to do, but the problem, I repeat, is that G2 and G1 are correlated. So I write BT3, and you will see that in this chapter, and even in the financial part, it's something that we are going to do several times, that is to make appear the increments of the brand motion. BT3, I write it as BT3 minus BT2 plus BT2. Okay? Why not? Why I do this? First, because I know BT2. BT2 is known from the previous step. I know BT2 and I obtain it from this step here. Okay? I obtain it from this step. I know where BT2 is. And so if I want to generate BT3, I have to generate this one. What is the distribution of this one? From the definition, it's N0 T3 minus T2. I can write it as the square root of T3 minus T2 G2, where G2 follows the N01. But what can you say about G2 and G1? Because if you use this, you only use the last part of the definition. The fact that the increment is Gaussian, this one. Okay? If I use this one, what can I say about G2 and G1? They have to be independent. Okay? And now I know exactly how to do the job. That is, in order to generate my G2 here, it has to be a N01, but a N01 independent from the first one. And I continue. Okay, for BT4, you can write BT4 as BT4 minus BT3 plus BT3, and you will have to generate a new N01 that is independent from the two previous ones. And this way, you are able to build all the points, okay, step by step. You have the BT3 that is here, this plot, BT4. And if I have a very small subdivision, you will obtain a picture as in the cover of the lecture notes. Question?
What was wrong is the G2, if it was BT3 follows and...
Nothing was wrong. The only thing that you have to keep in mind, if you do what I have done previously, that is to try to plot directly BT3. Okay? So all I have written is okay. BT3 can be written, let's say, as square root of T3 G2. The only difference I have between what I have written here and here is that I won't have the independence.
Why?
Because if you compute the covariance between BT3 and BT2, what is it? What is the covariance between BT3 and BT2? Let's do. First, I know that the ground motion is centered. So the covariance is just the expectation of the product. Okay, so how to compute it for Brownian motion? The idea, I repeat, it's exactly what I have done here. You make appear the increment because in the definition you have things about increments, bt minus bs, bt minus bs. So the idea here is to write expectation of bt3 minus bt2 plus bt2 time bt3. Okay, why I do this? Because I make appear here something that is independent of bt2. Okay, so the expectation of the product is the product of the expectation is 0, and it remains plus the expectation equal the expectation of bt2 squared that is equal to t2. So you see that they are correlated, meaning that this G2 here and this G1 can't be independent. So it's possible to do this this way. But if you do this, okay, you have to generate a G2 that have exactly the good covariance with respect to G1. It's possible, but in general, it's not what we do. In general, when you do simulations, okay, you generate, let's say, independent uniform or independent Gaussian, and you try to obtain what you want from these independent realizations. Okay? So it should be possible to do the job like this, taking into account the fact that G2 and G1 have a particular covariance. But if I want to overcome this problem, just write, in fact, what I have used here to compute, make the increment appear, and in this way I obtain here something that I have to generate. I know its distribution and I know the fact that it is independent. Okay? And I continue. And it means that if you have understood the principle, in order to generate my discretized trajectory, I just have to generate independent Gaussian and to apply this little trick here. Okay, so for BT4, I will write BT4 as BT4 minus BT3 plus BT3. I know BT3. I have to generate BT4 minus BT3, that is N0 T4 minus T3, that I can write as the square root of T4 minus T3 G3 that will be independent of G1 and G2, and so on. Okay, so if you have understood, to generate the trajectories of ground motion as an approximation, it's not more complicated than to generate independent N01. It's not more complicated from a numerical point of view. Okay. Is that clear? And typically, you will see that when we are going to work with the Black-Scholes model, so more or less what is the Black-Scholes model? But it's the exponential of the ground motion. So if you are able to generate the ground motion, you will be able to generate the trajectory of the risky asset in the Black-Scholes model, because you will just have to take the exponential of a ground motion up to some constant. Okay? And the fact that I am able to do this will make us able to compute prices in the Black-Scholes model using, for example, Monte Carlo approximations, because I am able to generate the trajectory of the risky asset. Okay? But we will come back on this point later. But it's really important to be able to generate or to approximate the trajectories this way. Okay? Is it clear for everybody? So it's the way I have drawn all the pictures related to ground motion in the documents. So for the moment, I have a look on the definition. Okay? I explained to you that if such a process exists, how to generate it. Okay? Now we are going to have a look on an equivalent definition of the ground motion in terms of Gaussian process. Okay? And why we are going to do this? Because it is this definition that we are going to use in order to prove that the ground motion exists. That is, it is possible to build it. Why such a process exists? A priori, I don't know. Why there exists a process fulfilling all these properties? We are going to see that it is the case. And in order to do the job, okay, in a nice way, we are going to use an equivalent definition. So it's the aim of the next proposition, that is an equivalent definition of the Brown motion in terms of Gaussian processes. So may I erase what I have written on the board? J'ai un petit tableau, donc dépêchez-vous pour écrire parce que sinon ça va être compliqué. It's okay? So it's the proposition 1.2.1. That tell you the following. So BT is a Brown motion in the sense of the definition 1.2.1, if and only if BT is a continuous and Gaussian process, and we have seen together how to characterize a Gaussian process. I know that I can characterize a Gaussian random variable from two numbers, its mean and its variance. We know that we can characterize a Gaussian vector from the mean vector and the variance covariance matrix. And we have seen together that in order to characterize the Gaussian process, we have to describe what is the mean function and what is the variance covariance function. So BT is a continuous and Gaussian process such that the mean function is equal to 0 and the variance covariance function is equal to the minimum between S and C. M of t, that is the mean function, is equal to 0. Okay, I use the notation I have introduced in the little part concerning Gaussian processes. The mean function is 0. Mt is just the expectation of Bt, that has to be 0. So in other words, my Gaussian process is centered. And this one, it's the variance covariance function, that is the covariance between Bt and Bs, has to be equal to the minimum between S and T. And if you remind the little part concerning Gaussian processes we have seen together in the chapter 0, I have said to you that if I want to be a variance covariance function, I need to check some properties. The fact that I am symmetric and positive, and I have proved that in this particular example, this one is positive. So come back to the chapter 0 to see that I have already dealt with this kind of mapping in order to prove that this mapping is positive in the sense of the mapping depending on two variables. So I have to prove this. And after, in order to build the Brown motion, we are going to prove that there exists a Gaussian process fulfilling all these properties. Okay? So I have an equivalence to prove, okay? First, we are going to suppose that these 4 points are fulfilled, and we are going to prove that I have this. And then we are going to prove that we have this, and check that all these points are fulfilled in the definition. Okay? So I keep what I want to prove on the board, I erase this one, and keep the definition of the Brown motion on the whiteboard. Okay. So I have a look on what I want to prove and check that all the points are fulfilled. So continuous, no problem, because continuity is one of my elements in my definition. Okay, so if I am a Brown motion, I am continuous, so I am continuous. I want to be that I am a Gaussian process. Okay? What is the definition? So Bt Gaussian process. What is the meaning of being a Gaussian process? What is the definition of a Gaussian process? Ce ne sera pas un vecteur gaussien, parce qu'un vecteur c'est un nombre fini de composantes, et là je suis un processus. But all the random vectors I can make from this process are Gaussian vectors. Okay, so to be a Gaussian process means that for all T1, so I can make them ordered, okay? For all T1 order. Better than this, so for all n belonging to n star, for all T1 Tn this way, I am interested in Bt1, Bt2, Btn, and I want to prove that this vector is a Gaussian vector. It is the definition of being a Gaussian process. All the vector I can build from myself is a Gaussian vector. Okay? And I repeat that I can always suppose this one, because if you don't have this, you reorder the component in order to have this one. Huh? And you know that if you change the component of a Gaussian vector, you are still Gaussian. You change nothing. So that's why I can always suppose that the time is this way. And why I impose this? Because you see that in the definition, okay, I have T is strictly greater than S. Okay, so I want to prove that Bt is a Gaussian process, and so I am interested in this one, and I want to prove that this one is a Gaussian vector. So just keep in mind the following. If I give you n Gaussian random variables, okay, n Gaussian random variables, there is one very easy case where the associated vector is a Gaussian vector. Which case? So if I give you n random variables, I put them in a vector. What is the case where you will have for sure a Gaussian vector? So for sure they are Gaussian. They have to be. But I need more if I want to have a Gaussian vector. If the components are Gaussian, it's not sufficient to have a Gaussian vector. It is necessary, but not sufficient. What you need to add in order to obtain, or one is, it's not the only possibility, but I said that there exists a nice situation, independent. If they are Gaussian and independent, the vector is a Gaussian vector. Okay? So if you start, because you know that linear combination of independent Gaussian random variable is a Gaussian random variable. But in general, it's not what happened. And here, you won't have the independence. They are not independent because they have a covariance that will be computed later on, but that is not zero. So here, I know from my definition that all these components, Bt1 is Gaussian from the last point, Bt2 is Gaussian from the last point, Btn is Gaussian from the last point, but I need to work a little in order to prove that I have a Gaussian vector. So, but the idea is to come back to the idea I have said previously, that if I have independence, it's easy. I have directly the fact that I am a Gaussian vector. If my components are independent, I have a Gaussian vector, but I have a lot of random variables that are independent here. Because in the definition of a Brownian motion, the increments are independent. So I said that I am interested in this vector, and I have a vector that is this one, that is for sure a Gaussian vector. This one is a Gaussian vector. Why? Because I know that all of them are Gaussian and independent. So using the point D and the point C in the definition. So here, this one, from the definition, is a Gaussian vector. Because of the fact that I have the Gaussian property of the increments, and also, it's important here that I have independence of the increments. So all these random variables here are independent because they are increments on intervals with an intersection that is at most a singleton. Okay? So I have this one, that is a Gaussian vector. And I want this one to be a Gaussian vector. Okay? This one is obtained easily, and now I want to prove that this one is also a Gaussian vector. So do you have an idea how to transform this one into this one, in fact? I know that the definition of being a Gaussian vector means that any linear combination of my components is a Gaussian random variable. So typically, if I transform linearly a Gaussian vector, I am still a Gaussian vector. Because linear combination of linear combination is a linear combination. Okay? So it means that from what I know, that is this one is a Gaussian vector, if I transform this one linearly in order to obtain this one, I will do the job. Do you have in mind a simple transformation that allows to pass from this one to this one? Identity?
No.
If you put the identity, you will. So if you apply the identity, that is the identity matrix, okay, you will start from this one and you will obtain this one at the end.
I said the BTIs are adding.
Yeah. So you mean that this one plus this one, this one. What do you mean?
Okay, no,
Dis-moi, j'ai pas compris.
no,
Sûr? Idée? Ouais. In order to transform linearly, we are going to use the matrix with constant coefficients here. And what is the idea that is below? But in fact, if I see this, this one is this one, so no problem. But if I do this one plus this one, I obtain this one. This one plus this one plus this one, I obtain BT3. This one plus this one plus this one plus this one, I obtain BTN. Because I have transformed. Okay? Yes. Yes. Okay? So if I do the sum of all of them, I obtain BTM. If I do the sum of the two first, I obtain BT2 and so on. Yeah. So it is sufficient to write. I can take a matrix. If I take as a vector this one, BT1, BT2 minus BT1, BTN minus BTN minus 1, and I want to obtain at the end the vector I am interested in. I can do exactly what I have done. Okay, so here, so I will have this one times this one has to be equal to BT1. So I put 1, 0, 0. Okay. For this one, I want this one times this one equal to BT2, but I put 1, 1, and 0. And at the end, all ones. Okay. I obtain something like this. So a matrix with on the diagonal I have 1, here I have 1, and here I have 0. You are sure in this way to obtain from this vector the one I am interested in. And so, since this one is a linear transform of this one by this matrix with constant coefficients, I have easily that this vector being Gaussian, this one is Gaussian by linear transform. It comes from the fact that in the definition of a Gaussian vector, it means that the linear combination of my component, any linear combination is a Gaussian random variable. So if you take a linear transform of a Gaussian vector, for sure it will be a Gaussian vector because the definition is based on linear combination of components. If you transform linearly a Gaussian vector, you are still a Gaussian vector. Okay? So by this argument, I have proved that, so continues from the definition, Gaussian process from this. Okay? And the idea is, okay, when I have a look on the definition, I see that I have here a lot of random variables that are independent. All the increments considered on, let's say, disjoint intervals or intervals with an interior that is empty set. And then I have naturally a lot of vectors that are Gaussian because I have independent Gaussian inside. And the one I am interested in is just a linear transform of this one that is obviously Gaussian by independence of the component. Okay? So I proved that the Brownian motion is a Gaussian process. Now it remains to prove that it is centered and that the variance-covariance function is given by what I want. It will be just a little computation based on these two. Okay, so may I erase this one and this one because I have to continue? Okay. So I erase. I am still in the same implication. Okay. So now I am interested in mt equal to 0 and gamma st equal to the minimum between s and t. So mt is what? By definition of the mean function, mt is equal to the expectation of bt. I know what is exactly the distribution of bt. It's n0t, so its expectation is 0. No problem with the mean function, okay? Because from the definition of the Brownian motion, bt is centered. Okay. Now I am interested in gamma of S and T, that is the covariance between BT and BS. And that is equal because I know that the expectation is 0, the covariance is just the expectation of BT BS. Okay, I have to compute this one. And the way to do, I will suppose that T is strictly greater than S. Okay? Oh, nothing to restrict, but yes, I have to consider 2K in fact. To be sure. If I have T that is equal to S, what is gamma of T? T. Yes, it's T because it's the variance of BT. And I know that BT follows N0T, so its variance is T. So when they are equal, I obtain the result I want. Okay? And now I just have to have a look on this case. Because by symmetry, okay, I can always suppose that the first time is always strictly greater than the second one. So T is strictly greater than S. So I am interested in expectation of BTBS. And I want to prove that this is equal to S. So how to do? Always make appear the increments. Always. You will see that when we are going to compute conditional expectation relative to the Brownian motion, it's exactly the things we are going to do again. Make appear increments because I know that the increments are independent. Okay, so it will be easy to compute. So I write as previously BT as BT minus BS plus BS. This way. Okay, and why I do this? Because I make appear here BS and something that is independent. Okay, so if I develop, I will do it last time, BT minus BS times BS plus the expectation of BS squared. What is the first one? The first expectation is 0, because the expectation of the product is the product of the expectation, each of them being equal to 0. And this one, S, because BS follows N0S. So its variance is S. At the end, I prove that if I suppose T is strictly greater than S, the number I obtain is the smallest, that is the minimum between T and S. So I have proved everything here. I have proved that a Brownian motion is a continuous and Gaussian process with a mean function equal to 0 and a variance-covariance function being the minimum between S and T. Okay? So it's an equivalent definition. And you will see, I repeat, that in order to prove, it's this characterization that we are going to prove. So I need now to prove the converse. If I have this one, I am a Brownian motion. So it's my hypothesis now. And now I have to check that the 4 points in the definition are fulfilled. Okay? So are you okay with what I have written here? Are you okay with what I have written? So I will erase this in order to keep place, in order to do the other implication here. Okay, I may erase. So this trick is really important. At this stage, know the characteristic function of a Gaussian and make the increment appear. If you have this in mind, you will have to use it for the final for sure. Okay? They are independent because I have this. BT minus BS is independent of all this one. In particular, it is independent of BS. So the expectation of the product is the product of the expectations, each of them being 0, because BT minus BS follow N0 T minus S. Okay? So I erase, and I prove the converse. I prove the converse. So I need to prove that the 4 statements in the definition are okay. So B0 is equal to 0. Why? So you tell me that I have this. Okay? What you can conclude about this one? Nothing. A priori, nothing. Suppose that you take a N01. The expectation is 0, but it doesn't imply that the random variable is 0 pure almost surely. If you want expectation equal to 0 implies the random variable is 0 pure almost surely, you need it to be positive or negative pure almost surely. If you can change sign, okay, you may have, it's what we call the symmetric random variable with an expectation equal to 0. Okay, so this one doesn't imply the fact that B0 is equal to 0 P almost surely. But we are not very far. So you have the idea to use this one. Let's do the same with this one. What can I add here? So I can keep this equality here and put a little something here. A square. In fact, I have this because this is equal to gamma 0, 0. That is the variance of B0. And now you can use your argument. Now I know that the expectation of the square is 0. The square being positive P almost surely, necessarily B0 is equal to 0 P almost surely. Okay, but I repeat, if you don't put the square, you can't conclude. It's possible to find random variables with an expectation that is 0 and that are not 0. Take any centered Gaussian random variable. Okay, okay, so here I have the variance of B0 because the expectation of B0 is 0. So this is gamma 0, 0, that is equal to 0 by definition. And so this expectation is 0, implying that since I have inside something that is positive, the fact that what I have inside has to be 0 P almost surely for sure. Okay? I repeat, the square is fundamental if I want to be able to conclude. Okay? So I have my first point. B0 is equal to 0. For the continuity, but I have nothing to say because I suppose it to be continuous here. Okay? So I have nothing to say. So let's do the last here. Because I have Gaussian hypothesis, okay, to prove, and I have a Gaussian process. So if I am interested in Bt minus Bs, what can I say about the distribution of this one? You don't have this, huh? It's what you want to prove. So your hypotheses are this one here. So why Bt minus Bs? Why you know the distribution of Bt minus Bs? I have an hypothesis here. I have a Gaussian process, meaning that any random vector made from this process is a Gaussian vector. So for example, you have Bt and Bs, the vector Bt minus and the vector Bt Bs, and you take here, you have a linear combination, the component. Okay? So this one is a Gaussian because Bt is a Gaussian process. Since you have a Gaussian process, if you take this kind of quantities, you are sure to be Gaussian. What is the expectation and what is the variance? So, if I am interested in the expectation, it's expectation of Bt minus Bs. It's just Mt minus Ms that is equal to 0. Okay, so I know that I have a 0 here. And then the variance. So I have the variance of a difference. Okay, it's possible for me to compute it. What is the formula for the variance of a difference? It's the variance of Bt plus the variance of Bs minus 2 times the covariance between Bt and Bs. It's because the variance is a quadratic form, or equivalently that the covariance is bilinear. So of course, when I have written this, I suppose my T to be strictly greater than S to be as in what I have here. So, what is the variance of Bt? I obtain it from this one. It's gamma Tt. That is T. The variance of Bs, S. So I have T plus S minus 2S, because I have supposed that T is strictly greater than S, and so the minimum between T and S is small s. So this is equal to T minus S. Okay, so I have the small d in the definition of the Brownian motion. The only thing it remains to prove is that Bt minus Bs is independent of FSB. And according to the remark I have done just after, it is sufficient to prove that Bt minus Bs is independent of any random vector made of Bu for u being less than small s. So I have on the board here everything, A, B, and D, it remains small c. Okay? So in order to do small c, I am interested in T1, Tn this way. I am in... Question? N'hésitez pas, hein. Si jamais on ne voit plus après pendant 6 semaines, vous serez dans votre lettre. Vous posez des questions en vrai. Via Skype, Zoom. N'hésitez pas, ne faites pas. Pas de question?
No.
So I take this instance, all less than small s. Huh? I use this, what I have written on at the beginning. That is, what is this? How to handle in practice this? That is to prove that bt minus bs is less than bt1 btn for all t1 tn less than s. In fact, it's exactly what I have written here. So I am interested in the vector bt1 btn, and my aim is to prove that bt minus bs is independent of the vector bt1 btn. Okay, and don't forget that I have a strong hypothesis that is to be a Gaussian process. An hypothesis that I have used for the moment only one time, that is here, to find the distribution of bt minus bs. Okay? And why it's important to have in mind the fact that I am a Gaussian process? Because you know, because we have seen this together, that in general, independence is something that is not that easy to prove, but in terms of Gaussian vectors, to prove independence, I have only to prove that covariance is 0. Okay? For Gaussian vectors. It's exactly what we are going to use here. So I want to prove this one. We are going to use, the main things will be that I have a Gaussian process. So I erase this. If you don't have questions. So I say two things, and it's an exercise we have done together. I said that bt minus bs, bt1, btn is a Gaussian vector. Are you okay with this? Because I have a Gaussian process. So if you made a vector from values of the process, you are sure to obtain any time, okay, a Gaussian vector. If you take a linear combination of these components, you will obtain linear combination of possible value of this process, so you obtain something that is Gaussian. So you have a Gaussian vector here, okay? So an hypothesis that is really strong if you want to prove independence. And we have seen a result together in the chapter 0 that, so maybe I can give you the name of this little exercise. It was exercise 0.3.1. We have done together. That tell me that if you have a Gaussian vector like this, in order to prove that the first component is independent of the remaining one, it is sufficient to prove that the covariance between this one and this one is 0, this one and this one 0, this one and this one 0. Okay, so I just have to compute the small covariance. So if I am interested in the covariance between bt minus bs and let's say bti, what is it? My objective is to prove that it is 0 in order to be able to use the result of this exercise, okay, that tell me that I will have the independence. So I use the bilinearity of the covariance to prove that I have here covariance of bti minus covariance bs bti. And what are each covariance? What are each covariance here? Don't forget that you have this one. So what is this? No, not BTI, it's a number of variance.
Yeah.
TI, the smallest instant. And here, the same. Because you have this. Ti is smaller than S, that is smaller than T. Okay? So I have done the job. I have proved that to say that I am a Brown motion is equivalent to say that I am a continuous Gaussian process with this mean function and this variance covariance function. After the break, we are going to prove the existence of the Brown motion in order to prove the existence of a process fulfilling these conditions. Question before the break?
How we can prove the stationarity of the equipment?
Oh, stationarity just means that the distribution of bt minus dbs only depends on the length of the interval ts. Okay, so you have it directly here because my Gaussian, okay, only depends on the distance between t and s. It's what we call stationarity, in fact. Okay, the distribution of bt minus dbs only depends on the distance between t and s, implying that B3 minus B2, B1 minus B0, B1 million minus B99 have the same distribution. That is the N01. Okay, that's what we call stationary. Questions about this proof? 10 minutes, not more, 10, okay? Here we go. So, I put here on the board just the equivalent definition of a Gaussian motion we have seen together. The one we have just proved, that is a Brown motion is a continuous and central Gaussian process with this variance covariance function. Okay? That's what I have proved. The idea is to build the Brownian motion. Okay? And the idea is to prove that there exists a process fulfilling the statement of proposition 1.2.1. Okay? So the idea is the following. In fact, so it's the null proof, okay, that is not the original proof of the existence of the Brown motion, that is, so I don't know if you have a chronology in mind, but the Brown motion was first observed and described in the beginning of the 19th century, okay? And the first rigorous proof of its existence is from the beginning of the 28th century, okay? So 1 century later. So what happened during this century? But the fact is that probability theory has started to be something that was important, okay, and well structured. And also the theory of Hilbert spaces. And in fact, the proof we are going to see together is based on Hilbert spaces. Okay? So the initial space we are going to work with is this one. So it's the set of the mappings from 0 capital T into R that are measurable, okay, and in L2 meaning that the expectation, but here if I don't precise, okay, I have just the Lebesgue measure on this space, that is the integral finite. Okay, it's the meaning of this space. S'il vous plaît. Okay. So you know that in this space I can define the norm. That is equal, so the square of the norm is just the integral of the square. And And I can also define the scalar product in this situation. The scalar product between two mappings in L2. Being the integral of the product. So we have this way a complete Hilbert space, okay, and so on, as you know. So I just check that I record. So I have a Hilbert space here of infinite dimension, and we are going to consider an orthonormal basis of this space. Okay? So let's see this way, E of n be an orthonormal basis. What is the meaning of being an orthonormal basis in this situation? I have ortho and normal. Ortho means I have orthogonality. That is, if I consider the scalar product between two elements of this type, I have something that is 0 if n is different from P, meaning that I have orthogonality in the sense of my scalar product. And if n is equal to P, I want the basis to be ortho and normal. Normal means that I have a vector of norm 1. I have this. The scalar product between two elements of this type is 0 if they are different, and 1 if it is the same element. Okay? So it is here, what I have written on the board is the fact to be orthonormal. Okay? Orthonormal means this one. Then I have a basis. And what is to be a basis? If f belongs to L2 of 0 capital T, I have two things. First, f may be decomposed on the vector of my basis. So that is, I can write f as the sum, that is an infinite sum, okay, of what? Of the scalar product between f and the element of my basis, okay, L2 time the element of my basis. Okay, it's exactly what you do when you decompose vector in r to the power n. You have n coordinates, okay? You can write the vector decomposing it as a linear combination of the vector of the natural basis in r to the power n. So I have this. So just a remark, I have an infinite sum. Okay? You know that the finite sum is just the limit of finite sums. So this definition just means that the limit of these sums, okay, exists, limit exists in L2 of 0 capital T. Okay, it is the meaning of writing the infinite sum as the limit of the finite ones, okay, the limit being in by the sense of the space I work with in L2 of 0 capital T. Okay, so if you want, I decompose my mapping, okay, on my vector basis, okay, that is an orthonormal basis. And what is interesting in this situation is that you can recover the norm of f from the coefficients in my decomposition. It's what you know if I am in R squared as the Pythagoras theorem. Tell me that the norm of f in L2 of 0 capital T may be written as the infinite sum of the square of the coefficients. Okay? I repeat that if you are in R square, you have a point with coordinate xy, meaning that you consider the classical orthonormal basis of R square. And if you want the square of the norm is just the square of this one plus the square of this one, that is x squared plus y squared. It's just the analogous of this one in infinite dimension. Okay? So it's what I need from Hilbert space theory related to this space. Okay? So copy this. You will need to have this in mind. Okay? And in fact, it will be the starting point of the construction of my Brownian motion. So are you okay with this? So it's just a reminder, you have already worked with this Hilbert space and I say nothing new. So you have in the lecture notes, okay, some example of such bases. Okay, you have bases using sinus and cosinus. It's what we call the trigonometric basis, the one you use when you do Fourier transform or something like this. Okay, you have other type of basis, but here I don't mind about what is precisely this basis. Okay, so I have this. Keeping in mind what are the underlying convergence. Okay. So the idea, there will be, starting from this Hilbert space, to be able to define my Brownian motion. So for the moment, we are very far. The only point we have in common is that, okay, my Brownian motion is defined at 0 capital. So I have this in mind, and now I will start my construction. Okay? So my Brownian motion is a Gaussian process. So in order to define it, I will need Gaussian random variables. Okay? So I consider the space L2 of omega AP, okay? And in order to build my Brownian motion, I will start from a sequence Gn, sequence of IID N01. So I start from a sequence of independent Gaussian random variable with mean 0 and variance 1. Okay? So, and intuitively, you are going to see that the construction of the Brownian motion is related to changing the initial element of my orthonormal basis by these Gaussian random variables. It's what we are going to do. Okay? Which way? I define this mapping that I call capital I, capital N. So capital I because it will be like an integral, let's say, okay? And capital N because for the moment, instead of working with infinite sum, we are going to work with finite ones, okay? So IN is what? Is something from L2 of 0 capital T into L2 of omega AP, okay, and that associates to any element of L2 0 capital T the following sum. The sum from n equal to 0 to capital N of what? But the element, the coefficient in my decomposition, that is f of n, and instead of multiplying by the element of my basis of L0 capital T, I put a Gn here. Okay? I do the job here. So I erase this So I will need it, but I have a small board, so it's the price to pay, okay? So I erase everything, I keep this in mind. And now, first we are going to study this mapping here. It has some interesting properties. I said that I have something that is linear. Are you okay with this? Why I have something that is linear? Well, because I have a scalar product that is bilinear. So you have f here. It depends on one coordinate. Okay, so the scalar product bilinear. If I have here a dependence in f that is just one component of the scalar product, I obtain something that is linear. Okay, so In is linear in the sense that if you consider In of a linear combination, you will obtain the linear combination of the In. Okay? What can you say about the distribution of this random variable here? What is the distribution of In of f? It's a Gaussian. I agree with you. So if I want to know it perfectly, I just have to know its mean and its variance. What is the mean? 0, because the GM are n01, so the expectation of the sum or the linear combination is the linear combination of the expectation, each of them being 0. Okay. What is the variance? Not yet. It's it's the truncated, not the norm for the moment. Okay, but I have the variance of a linear combination, and in the case of the independence, okay, the variance of my linear combination is the sum of the square of the coefficients multiplied by the variance of each term here. So the variance of this linear combination is just the sum n equal to 0 capital N of the square of the coefficients, because the variance of the GN is 1 and that the covariance are 0. So I have this. Okay? Why not? Now the idea is to justify that I can pass to the limit. I can pass to the limit. So I have defined I of capital N for a fixed capital N, and the idea will be to see what happens when capital N goes to plus infinity. So the idea is that I want to pass to the limit here when N goes to plus infinity. And I have to justify that it is possible to do this. That is, that I have a sum that is convergent here. Convergent in L2. Okay? So, I said that In of f, consider as this sequence here, is convergent in L2. So how to prove that something is convergent when you don't know the limit in the space L2 of omega AP? So in other words, when you are in a space that is complete, how to prove that someone is convergent? If you prove that you have the convergence of a subsequence, you will have the convergence of a subsequence. What is the definition definition of a complete space? Any Cauchy sequence is convergent. So to be convergent is Cauchy in this kind of space. Okay? So the idea we are going to prove that I have here a sequence that is a Cauchy sequence in this space. Okay, in L2. So I am interested in, so let's take N and P, okay, and let's consider that N is strictly greater than P. Why not? I am interested in let's take the square of the norm in L2 of omega AB. Okay? My aim is to prove that when N and P goes to plus infinity, I obtain something that goes towards 0. But what is this one? It is just the expectation of In of f minus ip, okay, is the sum that I can write it this way. This one. What I obtain, I am able to compute this one because keep in mind that my Jn are IID N01. In fact, it's a variance that I compute here. Okay? What is this? The sum. N equal to P plus 1 capital N of what? Of this one. Because the variance of the Gn is 1, and the covariance between two difference is 0, because they are independent Gaussian with mean 0 and variance 1. But what can you say about this one? You have already, you have again what happened on the board here. I know that this sequence is convergent here. Okay? This infinite sum is well defined, implying that the sequence of the partial sum is convergent, and so is Cauchy. This one goes to 0 when N and P goes to plus infinity. The argument is written on the board. It's because this infinite sum is convergent here. So the sequence of the partial sum is Cauchy because it is convergent. It's exactly what I have written here. When P and N goes to plus infinity, this term goes to 0. So I have proved that okay. So this one goes to 0, so this one goes to 0, and I have proved that my sequence is Cauchy, and so is convergent in this space that is complete. Okay? So I have the right to consider its limit. Okay? I have the right to consider its limit. So I will write it here. Now, I can define I, that is from L2 of 0 capital T into L2 of omega AP, okay, that associates to any f, not the finite sum, but the infinite one that I know that it is well defined now. Okay? Yeah. notation, okay, is for the limit when n goes to plus infinity of the finite sums. Always, it's the way we define an infinite sum. Okay, so to say that this limit exists, just to say that this infinite sum exists, just means that the limit of the finite sum, okay, is convergent and converges toward this term that is in fact the limit. Okay, so infinite sum has limit of finite sums. Okay, so it means that if I call this one un, this sequence is convergent in the good space. In the space here, I am interested in the space. I am interested in this one here. So this limit exists and is given by the infinite sum. So if the limit exists, it implies that the sequence is Cauchy. So un minus up, in which space here? So I repeat, just here you have a sum, okay, of numbers. And I know that, I have erased, but I know that the infinite sum is okay. The sum from n equal to 0 to plus infinity is just the integral between 0 and capital T, f square of x dx. So I said that if I have the infinite sum that is well defined, meaning that the limit of the finite sum exists, it implies that I have a Cauchy sequence here. I have a Cauchy sequence, and to write this, it's exactly what I have written here. Okay? I have a sequence that is just Cauchy. So this one is Cauchy, implying that this one is Cauchy in the space L2 of omega AP, and so I can consider this term here, that is the limit of in of f here, when n goes to plus infinity. I have the right to do this because I have proved that it is convergent when n goes to plus infinity in L2 of omega AP. Okay? So I define here this mapping, capital I, from L2 of 0 capital T into L2 of omega AP, that associate to any f this decomposition involving the coefficients in the decomposition of f with respect to the orthonormal basis of L2 0 capital T. So I keep this in mind. And now my question is what I can say about I. What can you say about capital I here? We have seen previously that In is linear in f. So since I is obtained passing to the limit in In, I will obtain the same linearity property for I. So I is linear. Okay? Linear. Because In is linear. And the argument is the same as previously, because here you have the scalar product that is bilinear, and f, okay, I have the dependence in f just through the first component of the scalar product here. So I obtain something that is linear. Second thing, what can you say about, so if f belongs to L2 of 0 capital T, what can you say about the distribution of IF? For In, we have seen together that In of f follows a Gaussian distribution with mean 0 and with a variance that is just the sum of the square of these coefficients. I erase this one and I have just the sum of the square of the coefficients. So the mean will also be 0. Okay? Why? Because I know that the expectation of all of them is 0 here. So I have the convergence in L2, as I have proved previously here. I have the convergence in L2, so I have the convergence in L1. And so the expectation of IF will be the limit of the expectations of the I and F that are all equal to 0. So Gaussian, we have said? Be careful, huh? Why I am Gaussian? It's true. Yeah, but be careful because you have an infinite sum, huh? You have a limit here. But you know the little exercise in the beginning of the chapter 0. If you have a sequence of Gaussian random variable that is convergent in L2, the limit is Gaussian. The proof is very basic. You use the characteristic function and you can pass to the limits in the characteristic function. If you have the convergence in L2, the first moment, that is the expectation, and the variance will converge, and so the characteristic function of a Gaussian that only depends on the mean and on the variance will also converge. Okay? So from the fact that I have the convergence in L2 of In of f, I know that since the In of f are Gaussian, as finite sum of independent Gaussian, I am sure that this infinite sum follows the Gaussian distribution with a mean that is 0. And what will be the variance? The variance, so I have proved that the variance of this one is just the sum of the square of the coefficients, and I can pass to the limit because if you have the convergence in L2, so if xn converges toward x in L2, the variance of xn will converge toward the variance of x. Okay? And so here I have what? I have the sum n belonging to n of f of Tn squared. But do you remember what is this? So it's the norm, the square of the norm of f in L2 of 0 capital T, that is just equal to this one. Okay? I have this. So I is linear, and I of f, using this convergence in L2 I have proved, is a Gaussian random variable with a mean that is the limit of the mean of this random variable and a variance that is the limit of the variances of these variables. So I have this one. Okay? Last little property fulfilled by these two. Can you tell me what is the covariance between I of f and I of j? So in this case they are central, so the covariance is just the expectation of the product. What is this? You have the variance of this one, that is this one. What may be the covariance between two of them? The covariance, but the variance is just the covariance of this one, and I know that it is equal to this term here. What is the covariance? The integral of the product. Using exactly the same argument as the one that I have used in order to obtain this formula. Okay. If you are not okay with this one, you consider In of f and IP of j. You compute the covariance, you are able through this formula because you have independent Gaussian. And you pass to the limit and see what happens. You obtain exactly, in fact, the scalar product between f and j in L2 of 0 capital T. You are going to tell me why we are going to do all these things, okay? Keeping in mind that I want to prove that the Brownian motion exists. But now I have everything. So in fact, you will see in the lectures note, so I don't follow the order of the lectures note, but capital I, okay, is what we call the Wiener integral. The Wiener integral. Wiener was the first mathematician to prove the existence of the Brownian motion using rigorous arguments. You have capital I, that is called the Wiener integral. And you will see that in a few minutes, the notation that we are going to use for I of f would be this one. But it's just a notation for the moment. Okay? So, where is my Brownian motion here? Well, I can give you a definition of the Brownian motion from what I have done now. Okay? The Brownian motion is defined this way, and we are going to check that the definition I give you is compatible with the proposition 1.2.1. I define Bt, okay, as I of the indicator function of the interval 0t. So it's a definition that I propose, okay? Definition. And my job now is to prove that if I define Bt this way, I define one motion that can be equivalently described as continuous Gaussian process with mean function equal to 0 and variance covariance function equal to the minimum between S and T. Okay? So in order to check that this Bt gives rise to a Gaussian process, we are going to prove that the equivalent definition proposed in proposition 1.2.1 works. That is, we are going to prove that I have a Gaussian process here with a mean function equal to 0 and a variance covariance function that is equal to the minimum between S and T. So why I have this? First, I want to prove that I have a Gaussian process. In order to prove that I have a Gaussian process this way, I have to take any, okay? So in order to prove that I have a Gaussian process here, I have to consider this kind of linear combination. With n belonging to n star and with, or n, and T1 Tn belonging to 0 capital T to the power n. My job, if I want to prove that I have a Gaussian process, that is any random vector that I can build from this process is a Gaussian vector, that is any linear combination of their component is a Gaussian random variable. So my job is to prove that I have a Gaussian random variable here. And why I have a Gaussian random variable if I do this? Keep in mind that I have done all this job for this. I can write this as the sum from I equal to 0 to n, lambda I of indicator function of 0 ti. Okay? But what can I use? What I know about I is linear. Okay? I is a linear mapping. So I can write the sum of the lambda I bti as I of the sum of I equal to 0 to n, lambda I indicator function of 0 ti. What I know about capital I is that capital I of anybody is a Gaussian random variable. So you have here something that is necessarily a Gaussian random variable. So the fact that Bt is a Gaussian process just comes from the fact that I of someone is Gaussian and that I have the linearity in order to write this linear combination of I as I of the linear combination. Okay, so you have defined here something that is a Gaussian process this way. Because if I take this linear combination, from my definition they can be written this way, and capital I is linear. So I can make the sum enter the capital I. And this one is necessarily Gaussian because, that's what I have proved previously, I of someone is a Gaussian. So I of this one is a Gaussian. So I have a Gaussian process. Now it remains to check that my mean function is the good one and that my variance covariance function is also the good one. Okay, what is the mean function? So what is the expectation of Bt here? It is the expectation of I of someone, that is here the indicator function of 0t. And what is the expectation of such an object? Zero. So the mean function is the good one. It remains to find the variance covariance function, that is to compute the expectation of the product, because the expectation is 0, so the covariance is this one. Okay. What is this? From my definition, it's the expectation of I of the indicator function of 0t multiplied by I of the indicator function of 0s. But what I know from the job that I have done previously that the expectation between the product is just the integral of the product. So what I have here is just the integral between 0 and capital T of indicator function of 0t u, indicator function of 0s u du. What is this integral? Or what is the product of the indicator function? It's the indicator function of the intersection. And what is the intersection in this case? It depends on the smaller one, but in any case, this is the indicator function of 0, the minimum between t and s. At the end, I have the minimum between t and s. So I have proved that my Bt is a Gaussian process from this argument here. Once I have done the job with defining capital I, it goes very quickly here. So Bt is a Gaussian process from this one. Its mean function is 0 and its variance covariant function by construction is equal to the minimum between t and s. Okay? So if I have a look on this definition, I have almost everything. I am a centered Gaussian process with covariance function equal to what I want. But the only thing it remains to prove is the continuity. It's a little bit technical, so I won't do it. But believe in me that I have something that is continuous. Okay? It's not that long, so two possibilities. I can do it by myself and the proof is a little bit long, or I can give you a result that will ensure that I have the continuity, but in both cases, okay, if I admit a big theorem or more or less the same. But what is important here, because it's something that we are going to use later, is this construction here. This construction that allow me to obtain quickly up to the continuity the Brownian motion. Okay? But don't worry, in the chapter 2, I will have other tools in order to prove that I have the continuity of these things. Okay? Through the Ito integral, but for the moment I don't want to spend time, so okay, it's already technical a little bit, so. But defining this capital I here, I define this way the Brownian motion that fulfill up to the continuity, if you believe in me, all what I need in proposition 1.2.1 to be a Brownian motion. Okay? So it means that I have a nice formula for BT, because keep in mind that I was defined in a particular way. So, are you okay with my argument? So, if you have understood this, after, you have nothing. I just think about this one, okay? But all the features of proving proposition 1.2.1 comes from what I have proved for capital I. Okay? Questions or no questions? Okay? So, I erase this part here, if you are okay. And now, I have a nice formula to propose you for BT. BT is equal to what? It's the sum from n equal to 0 to plus infinity of what? The scalar product between this one and the element of my basis, that is just integral between 0 and t, Tn of s ds gn. And if I give you a particular orthonormal basis of L2 of 0 capital T, you have a kind of closed form formula in order to define the Brownian motion through an infinite sum. Okay? So just a remark concerning the continuity. So I suppose that long time ago, maybe you have studied infinite sum of mappings. No? Série de fonctions? Long time ago, whatever, but what I need to have in mind is that what I have inside here is something that is continuous. It's the integral depending on the upper bound of something that is in L2 of 0 capital T. Using the Cauchy-Schwarz inequality, I can prove that I have the continuity of what I have inside. My only problem is to prove that, okay, the finite sum are continuous, that the limit is continuous. And you know that even if the sum is convergent, it's not sufficient in order to have the continuity of the limit. So I don't want to enter into detail, but you need to have convergence uniform on all compact sets and something like this, but whatever, okay? But just to say that I have an infinite sum of continuous mapping. If I do classical job, let's say, it should be possible to prove that the infinite sum is itself continuous, okay? I won't do, I repeat, because it's not that easy, not that complicated, but not that easy. So, in the lecture notes, I give you some formula for particular choice of this one. If you take the trigonometric basis, you will recover the first definition of the Brownian motion proposed by Wiener in 1923. So without using all these technical tools that are coming from Hilbert space theory, that are in fact modern mathematics, okay, I just prove that it works. Okay, so we study the convergence, okay, of this one using basic tools, okay, and prove that it fulfills all we want. But you have other candidates, okay, in order to obtain nice approximation of the Brownian motion. And typically, if I give you an orthonormal basis, if I want you to plot BT, what you are going to do, you are going to take a truncated sum here for a very big index, and plotting this, you will have an approximation of the Brownian motion. So you have example in the lectures note how to approximate the Brownian motion, not the way I have done previously considering a discretization, but using this kind of infinite sum, okay, in order to obtain nice explicit formula. Okay? So I continue with this notation here. In order to explain to you this one that is also a notation. Okay? So I have this definition of my Brownian motion. If I come back to I of f was defined as the infinite sum of what? Of integral between 0 and capital T of f of s Pn of s ds multiplied by Gn. This one. Okay? Where this one is a particular case taking for f the indicator function. Okay? So let's admit with me the following. I don't say that it is rigorous, but I write the following. I say that d of bt from this formula, I write it to be intuitively as the infinite sum of what? So I compute the derivative of this one, that is just Pn of t dt gn. If I take the integral between 0 and capital T of f of, let's say, t dbt, using the intuitive relation deduced from this one, I obtain what? I obtain this one, that is the sum of what? I complete integral between 0 and capital T, f of t, Pn of t, dt, gn, that is simply I of f. That explains to you why we call this I of f the integral of f with respect to the Brownian motion. So it's not something that is rigorous, what I have written, but just a way to define what we call the Wiener integral. And if you want to see it in another way, just say that, okay, I have an integral here. If I plug inside the indicator function, what I obtain here will just be the difference of the Brownian motion, that is bt minus b0, that is given by bt. Okay? So you have the Wiener integral here. So I have built the Brownian motion, and in fact I have built more. I have built the Wiener integral. Okay? So my job will be now to, once I have defined the Brownian motion in a good way, will be to study the properties of the Brownian motion. Okay? So in fact, I will never come back to this definition. Here it was just to show you that it exists and the way I can build it, okay, using Hilbert space theory. But you can find in the lectures notes a proposition. So what I have done is explain not in the beginning of the chapter 1, but it is explained quickly with less detail than what I have done in the part 1.3.7 that is called the Wiener integral part, okay, where in fact I do exactly all the job I have done here, but very shortly, in fact. You have more, well, I give you directly the formula, okay, this one, okay, I have justified on the board here. And you have so several properties for this Wiener integral, okay? So you will see that my job now will be to prove properties for the Brownian motion. And since the Brownian motion is a very, very particular case of the Wiener integral, I will have the analogous for the Wiener integral. Okay, that is the Wiener integral, okay, will be a Gaussian process also with a particular mean function equal to 0 and a particular variance covariance function. And all the properties we are going to see now about the Brown motion will be possible to have them for the Wiener integral also. Okay, so when I will come back to this proposition, since I have done the construction, since I have defined the Brown motion this way, and since we are going to study the Brown motion, I won't do the proof of this one. It will be an exercise for you, but in fact, everything was done today in class together in order to prove this. Okay? So, in order to conclude the today's session, okay, so I forget this construction of the Brown motion. So you have nice formula for the Brown motion in the lecture notes, and we are going to start to study its properties. Okay, so we are going to study this property in relation with martingale's property. In fact, the Brown motion itself is the martingale, and some transform of the Brown motion are martingales. And we are going also to study the trajectories of the Brown motion. We are going to prove that, well, from the definition, the Brown motion is continuous. We are going to prove that the trajectories of the Brown motion are nowhere differentiable, something that is a priori strange, okay, but that we are able to prove. So you will have here an example of a mapping that is continuous everywhere, but differentiable nowhere. We are going to prove that the probability that the trajectory of the Brown motion is monotonic in no interval is equal to 1, meaning that even if you take a very, very small interval, it's not possible for the Brown motion to be increasing nor decreasing, meaning that you have, okay, deep variations even if you consider very, very small intervals, okay, and all properties of this type, okay. So I will finish today by the proposition 1.3.1. So, and as I have said to you, so we don't have class next week. The 28th I am not here, so what I will do, I will record a video concerning, okay, the technical property of the Brown motion. I will do a 3-hour class that will be available in 1 week. And we will do a Zoom session during the holidays if you have some questions concerning what I have done. Okay? So, I erase the blackboard. So now, okay, little properties concerning the Brown motion and martingales. So something that you have to know. So it's the proposition 1.3.1. Okay, so I have bt square minus t. So bt square minus t and exponential theta bt minus theta square t over 2 for all theta belonging to R. But here I have 3 examples of martingales. So with respect to what? I need a filtration. If I have a martingale with respect to the Brownian filtration. F, T, okay. So it is a little exercise concerning, in fact, martingales, and I will finish by this today, proving this true. Okay. So first of all, remark that all of this process are function of bt, so are ft b measurable. So I have adapted processes here. In the definition of a martingale with respect to a filtration, I need to be adapted to the filtration. It's exactly what I have. Okay? Bt, of course, is adapted to its natural fluctuation, but here I have bt square minus t that is just a mapping of bt, here also a mapping of bt, so all of them are FTB measurable. Okay? So they are adapted. So I can also see that the Brownian motion bt is Gaussian. Okay, so b is in L2, so it is in L1. bt square is in L2, so it is, and b is in L2, so bt square is in L1. So I have mappings that are in L1, and in the definition of being a martingale, I need to be in L1 because I want to be able to compute the conditional expectation that is defined for a random variable in L1. And why this one is in L1 also, this exponential? Why this one is in L1? What is the Gaussian density? Gaussian density, you have inside exponential minus x squared over 2. So if you integrate a mapping that is just the exponential of a Gaussian, from the fact that the density of a Gaussian has the form up to constant exponential minus x squared, you are sure to obtain something that is finite in expectation. Because you will multiply an exponential that may be a positive or a negative exponential, whatever, but you will integrate with respect to the Gaussian density that is of the form exponential minus x squared over something. Okay? So exponential multiplied by exponential minus x squared, the exponential minus x squared wins, and so you have an expectation that is finite. Okay? So for bt, so I suppose t to be strictly greater than s, and I want to compute expectation of bt given fsb. I want to compute this conditional expectation. So if you have understood what I have said before, what I have to do, make a Pierce increments, always. So, in order to compute this conditional expectation, I just write bt as bt minus bs plus bt. And why I do this? Because you will have here something that is independent of FSB, and so the conditional expectation will just be the expectation, and here you have something that is FSB measurable. Okay? I have said everything, so I obtain what? BS. Because bt minus bs follow n0 t minus s, so the expectation of bt minus bs is 0. Okay, so I want to be more precise, I will write it this way, 0 plus bs. And now I just use what I know about conditional expectation. The conditional expectation of something that is independent is just the expectation, and my expectation here is 0 because I follow the n0 t minus s. So you have the proof of the fact that the Brownian motion is a martingale itself. Okay. bt square minus t, I will do exactly the same. If I want to compute this one, we are going to make appear the increment, as usual. Now, here it's a little bit more complicated because I have the square, so I have several ways to do this. And the best way to do this will be to use something we have seen together in the chapter 0. Because, what can I write here? I can write this one here as phi of bt minus bs and bs, where phi of xy is just equal to x plus y squared minus t. Okay? So it's a reasoning I can do for the previous one also, but in the previous case it's easy to compute everything directly. Okay, so I don't need this. And what is interesting, once again, is that I have exactly the same thing as here. Here, you have something that is independent of FSB and something that is FSB measurable here. But we have a result in the course, in the chapter 0. In the chapter 0, I have explained to you how to compute the conditional expectation of a mapping where I have a part that is independent and a part that is FSB measurable. So I don't remind the name of the proposition. I don't have it here, but I will show you it. I have the lecture's note. It's the proposition, the last one concerning conditional expectation. Where it was, this one. Proposition 0.4.3. I have said to you that I will use a lot of time this proposition, but now it's one time. I have a part that is independent, a part that is measurable. So if you come back to this one, I have a part. So x is independent of j, y is j measurable. I compute the conditional expectation with respect to j. It's exactly my thing here. And what I obtain the fact that my conditional expectation will be a function of the measurable part that is f of bs, where f, let's write it this way, f of v is equal to the expectation of phi bt minus bs. I come back to the case of an expectation. Here. Expectation that I am able to compute here. What is this expectation? This is my phi that is defined this way. So in fact, this conditional expectation may be written as a function of bs. The function given by this expression, it's exactly the proposition 0.4.3 we have proved together. And what is this f of z? F of z is equal to the expectation of bt minus bs plus z square minus t. Okay? Well, it's not that complicated to compute because I know exactly what is the distribution of. So I have bt minus bs plus z. What is the distribution of this one? Gaussian, with mean z and variance t minus s. Here it's the expectation of the square, that is the variance plus the square of the expectation. And f of z in this situation is equal to what? It will be equal to t minus s plus z square minus t. And so if I replace expectation of bt square minus t given fsb is equal to this mapping where I plug instead of z bs, that is bs square minus s, and I have proved that bt square minus t is a martingale because the conditional expectation of bt square minus t given fsb is equal to bs square minus s. Okay, so you have proved here that this one is a martingale. Okay? So at home, because it's time now, just to finish, do this one by yourself to prove that this one is a martingale. The same methodology apply. You are going to make appear the increments and you are going to use proposition 0.4.3. Okay? In order to compute the associated capital F in the case of the last situation, You will need to be able to know the moment generating function of a Gaussian that you know from the characteristic function of a Gaussian. So try to do this one by yourself. It's a good training concerning what I have previously done and this proposition 0.4.3. Okay? See you.